Hello guys, it's time for another OptiNews. It's been a long time since the last one, maybe it's a month ago, and I thought it would be good to show you some progress on things I'm working. Now, compared to the previous OptiNews, I don't have something entirely new to show, even though I would have liked to work on some other project than the software 3D engine I was working before. It's the same engine with some improvements, but the biggest thing is that I went into a frenzy of porting it in a lot of other machines. And I was curious to see it running in some old school 32-bit machines and compare the speed. I was really curious to compare the speed between the 3D and the other machine, and we will see it. And I guess in the future, now that I have fulfilled my curiosity, I might be improving the engine or working on some other things. But for now, you're going to see the same Guro and environment map objects running in multiple platforms. But it's still interesting. And I think I did minimal progress in the engine itself. I corrected few bugs. There were some black pixels between the polygon edges that you could see sometimes, but it was rare, but you could see it. I fixed things like that. And I don't remember if I improved. Maybe I didn't improve the speed on the 3DO. But I'm going to run it on the 3DO again. So that I hope this is the one. I'm running it in Phoenix because the accounting for cell cycles is more accurate. Not exactly the most accurate. Is it running? Maybe it's pre-calculating things. Takes a long time now. Okay. And we are going to run everything in the real hardware too later. So let's compare the 3D version on the emulator. Let's see the keys. Okay, this is the auto rotate key. We have the Guro cube. There are no gaps. There were on the corners of the cube sometimes. You could see a black pixel. This has to be with precisely the pixels of the polygons at the edge if there is underdraw or overdraw. I don't know if there is a bit of overdraw, but there is no underdraw. So the frame rate is it's variable depending on how the cube looks. And now the cube is closer to the screen. And it might be worse on the real 3D. Yeah? This is the texture mapped, but it's all unlit. It's not shaded. This is the shaded version. It goes much slower at this size. The 3DO has the weakest CPU from all the machines I have tested. And now I've done something else. With a button, I will switch to this object, which is a bit more complex, the Guro shaded version. We are in 8-bit per pixel mode, by the way. This is the texture mapped. You see the frame rate, it's a bit variable depending on how it looks, but we can compare. And it is quite slow with big object. Now, in the same executable I can switch to the 16-bit object. I have made it so that I don't have to compile different executables for different meshes and different objects. So that's the 16-bit Guro cube. This is the pure software rendering. It's not the one I did with the Half-Life using the Cell engine and Half-Life. We just compare the CPU now. You can see the frame rate there. This is the environment mapping, unlit, and this is the shaded version. This is pretty slow here. And this is the wireframe, the anti-aliased wireframe. It's pretty fast, but it's a simple object. Now we go to this object, very complex, very close to the screen. It suffers even more. It might look slower than my last OptiNews, but that's because the object is closer to the screen. It's much bigger than before, and this is really suffering. Single digit frame rate. I haven't done anything besides fixing a few bugs and make the keys being able to switch through both meshes. And this is the wireframe. Now, for example, you can zoom out. Now, if you put it here, even this one is doing much better, but it's far. And one final thing, this engine right now, in all machines, it's not accounting for object clipping. It doesn't do any clipping. So if I move very close, you will see crashes and you will see some interesting visuals. Yeah. So the next thing and the most interesting thing, and maybe I'll show a bit of code in this one too, was the PC-FX. I mostly spend most of my time in the PC-FX because it has a special hardware. And I even tried to find better ways to bleed in the video RAM because the way it's doing it is pretty slow. And I will tell you something. What you see in the emulator is much faster than the real hardware. We will try on the real hardware later, especially the 16-bit mode. I realized I thought I had a problem with my code. I thought there was a bug, but I think I never tried it before. The 16-bit full copy of the frame buffer would drive the frame rate at 8 frames per second on the real machine, while it was like 70 frames per second on the emulator. The 8-bit mode on the real machine is doing 30 frames per second. That's the bottleneck. You cannot bleed high. But this is if you bleed the whole. I'm going to show you what I did. I'm going to show you the versions on emulator, even if they are pretty much faster. Now the CPU is really good. The CPU boosts it up, but unfortunately, so that's the 8-bit version. Ah no, that's the 16-bit version. Hold on. Ah yeah, you're right. Oh, what? Maybe that's the 16-bit version. Oh, you will see me compile it then. I don't know what happened. I prepared that. Maybe it's the other way around. Oh god. My test CDQ, my test CD. Okay, fuck this. You will see me compile it twice. I used to have this. I don't understand it. I even have it here. I was going to. How did I thought? I don't know. I'm using WSL Ubuntu Linux because I don't have a real Linux on my machine. No. let's see. I think this has to be the 8-bit version. Please don't destroy my. I thought I prepared for this video. Ah, finally. The 8-bit version, 60. Okay, this is faster than the real machine, but in the real machine it's still pretty good. So maybe it's better to see it in the real machine. But anyway, this and this, the Gurod texture, then this object, and you have the same thing. Where are the buttons? If you go like this, you're going to totally crash it. Funny stuff. Now, I have to separate executables for this one because I'm initting the video RAM at the beginning and I don't have one executable for both. On the 3DO it goes easier because each different video mode is really a different texture with a different bit depth. The video mode is the same, but you have an 8-bit per pixel texture and 16-bit per pixel texture. But here in the other ports I'm going to show you, I have 2 executables. This one looks better. Now this, for example, okay, this is the 16-bit. For example, if I run this on the real machine, I think I get 15 frames per second. Oh, and I will show you something, even on the real machine. And but first, okay, first let's cycle through all of it. Also, you see the color gradient is a bit off. It's weird. I don't know if it is because of the YUV color scheme of the machine. It doesn't have RGB, it has luminosity and UV for the colors that are 4 bits per pixel each, and the Y vector, the luminosity is 8 bit. And I do some conversion from RGB to YUV, but not on real time. But when I create the palette, the lookup table, actually it's 16 bit. There is no palette here. There is a lookup table. And here is the environment map, and here's the shaded environment. The interesting thing is the environment map is a bit fast, the shaded environment map, because on 3DO and other consoles that have RGB, you have to read the texture, 16-bit texture, extract the RGB components, shade them separately, combine them back and write them back. But here, because the color component, the color scheme is YUV, and the Y is affecting the luminosity. It can make a color pretty dark, or it can make it as bright as white. So I interpolate the Y component, that is a byte, and I just write back. I don't need to break the 3 channels and do stuff. So that was pretty interesting on this machine, because suddenly you have a smooth shading texture that doesn't take as much CPU. And this is the, yeah. And how about, okay, here's the other object. It's a bit heavier. That's how it looks with shading. Colors can be a bit different. Oh, I see. Maybe I didn't fix it. Do you see the black pixels? Yeah, I might need to stop it for you to see. See, my mouse is not. You see a black pixel on the right side, on the object. when you move sometimes. Oh, hold. Wrong button. See, on the edges, in the upper left side. I think I fixed this. These are things that polygons are not fitting. I will see it. I think I fixed it in all ports. These are annoying. Anyway, let's... That's the wireframe. Now, the other thing. I'm gonna tell you now about the other thing. So, look what happens if you go far away. No, let me find the keys because... Not this one. Okay. Look how fast. And it's not only because the object is small. I'm doing something. I will maybe whenever I'm about to render an object, I will find the smallest region. Where is the color? I will find. Okay, it's smaller than this. And I will have a smaller buffer. I think I have talked about that before. I do it on the 3DO because I use the cell textures. And I have a smaller region, a variable region of this frame buffer. So I will render in a smaller region and then render that. I would render that to the back buffer of the machine, of the PC-FX, and then render the back buffer on the big screen. But now I will render this region directly to the video RAM. So there is no, the back buffer would be something that fits the whole screen. But I don't have a big back buffer now. I have a smaller variable region. I have a big memory array that it's variable in size. No, it has a much bigger size, bigger than the whole screen. And I save I render my data there, and then I take it scanline and by scanline and render it on the real PC-FX. Previously, because the output to the PC-FX frame buffer, especially in 16-bit, it was very slow. Previously, it didn't matter if my object goes far away, it was still 8 frames per second on the real machine, and it was 70 frames per second on the emulator here. But now, yeah, because I would render the whole frame buffer back, and the 16-bit for some reason was 8 frames per second. The 8-bit frame rate was 30 frames per second. It was 4 times faster, not 2 times faster. That doesn't make any sense. And even the 8-bit had a bottleneck of 30 frames. And this is something I don't understand. And I thought at some point I have some bug in my code in the way I access the frame buffer. But actually, I will show you a bit of... I used to have... See, I commented this out. This would write the whole frame buffer to the King K RAM. And I even explored a lot of functions, but they are all slow. Because someone told me there are different ways to access the frame buffer. And the usual way... I tried a lot of stuff. The usual way is to use an out to this address. And it has to be a 16-bit out. Actually, that's not really true. No, the reality is you cannot do out B. This is not going to have an effect. You have to do 16-bit writes. Or maybe you get double pixel. This is also a problem with the Game Boy Advanced, I think. So you have to access 16 bits at a time. Also, I realized that in my other test, if I access 32 bits at the time, it works. Okay, it works on the real hardware, it works on emulator, it works on the real hardware. But the frame rate, you know, this one would give you hit a bottleneck in the 8-bit per pixel mode, a bottleneck of 30 frames per second, but this one would give you 32, 31, 32. It gives you slightly better, but it still hit the bottleneck. Now, someone told me, one other thing is that instead of out, there was another way to access, to write in the video RAM by memory mapping to certain address, BC000000, and it worked. But it has the same speed as doing it with an out. And this means that if you do a continuous loop and write to BC000 from BC00 to BC-FF, they all mapping, they have made it that they map in this register. And you have to put register 10 this value for some reason to select the KRAM write register. I was missing that and it didn't work at first. I was like, what the hell? And this worked, but it gives the same. It's the same thing as making an out. And someone told me that was the last experiment. And I will stop. I have unrolled that stuff. Where is it? Sorry. Ah, yeah. Is it this one? See, those are the machine has 32 registers, but you have there 26, 27, 28, 29, and 30. There are some special commands, which is this is like a mem copy, but it works on bits. It's bit string instructions, and you can, of course, now I'm setting R0 register always has the value 0. It's the 0 register. So I'm setting R26 and R27 to 0, so that I start from bit 0. I don't start from an offset bit. But you can say start copying from that address from the 11th bit to that address at the 17th bit. It was a copy on the bit, but I didn't need that. I put those 0 because I just need to copy full byte blocks or 32-bit. I think the addresses have to be 32-bit aligned. So someone told me if you use that, it might be faster. It wasn't faster. It was even a bit slower, like from 31 frames to 28 or something. And even in the emulator, it was slower. But anyway, I was explaining what I have a function for the 8-bit version because in the 8-bit version it seems slower, but for some reason, if you write byte by byte, the byte order is flipped and you have to do some arithmetic. And that didn't affect the performance because I had the bottleneck without anyway. So whether I use one of these functions and my 8-bit mode is wrong, the pixels are wrong, or I use the other one, I get 30 frames. Anyway, but look, I have commented this out because and also I'm not writing the display anymore. It's a hack. Because of this bottleneck, I decided to do what I do on 3DO, to have a sub-region, a smaller buffer where the object fits, and render that directly. On the 3DO, this is on a cell texture, and I render the cell texture as a sprite. Here I have to manually do it, so that takes a bit longer than I thought, but sorry. But it's fine. I'm not going to show code from other machines. So somewhere in my engine, after I used to have the render soft buffer to screen. I commented that out. This will render to the screen. This is the full frame buffer. Okay, but now I have render soft buffer to. Soft buffer is the smaller buffer that fits exactly the object. This is variable. If the object zoom too close into the screen, you have a bigger. If it's far away, it's a tiny thing to copy. But it's copied directly to the screen. No intermediate full frame buffer. And that's the only way to get some speed on the PC-FX. Render soft buffer to screen directly. And this is using. This is a loop on vertically and horizontally. And I have two versions. I wrote another function. It's doing basically the same. I don't unroll now because it's more variable how much the line is. In the full frame buffer, I knew that my frame buffer is 256 pixel by 256, which always divided by 4, or by how many times I unroll that, 16 or whatever. So I did some unroll and know that this is not going to. But this one is variable. Now, the lines are still 32-bit aligned. They can be 4 bytes, 8 bytes, 12 bytes, and so on. But I can't unroll 4 times. I would have to code something more, count the times, unroll some and complete the rest. But I didn't want to bother at the time, and I wrote something, a more simple loop that I out a word, I see. Here I out to, because here this version is for the 8-bit mode. So this is going to out directly to the video RAM separate scan lines. And only from the smaller software render buffer region. For the one I render the object. That is a smaller and variable one. Anyway, that's it. I discussed this too much. We are going to see the speed on the real machine for that one. But now let's go. Okay, the next machine. Okay, the next machine I ported it. I wanted to port the engine on a 386 computer. Now this is DOSBox 6 and it's not precise. I can put emulate a 386 DX33. My target machine at my home is a 386 DX40. Really, with a Cheng Lab size graphics card. Now, this one is DOSBox, so it's not accurate, but we will run it here. I have two versions, one DJGPP, one Wattcom. For some reason, the Wattcom is again a bit faster, but the DJGPP is not that. I used to have some problems with memset and memcopy, but I think I replaced. It doesn't matter, I'll run one of them. Oh, the frame rate, it's a bit dark, but we'll see. In fact, I'm under the impression that it's faster on my 386 DX40. It doesn't matter, let's just check a bit. It definitely is. Now, this is 8-bit mode. I don't have a 16-bit implementation. I just do a regular VGA mode. And now this bigger object. Still, for a 386, I wasn't expecting to see such kinds of rendering on the. We used to see demos on the 386 with flat cubes and flat polygons. It was rare to see a good raw environment map. Although it's a simple object. 11. I think this one is doing 15 frames on my 15 frames per second on my 386. And also if you dare to, where are the keys now? I'm trying to, okay, hold on. Okay, yeah. I don't have good key emulation. Let's try to zoom. Crashed. Just froze. Oh well. And last but not least, I decided to port it on the Game Boy Advanced. I will also run this on the real hardware later. So, Game Boy Advanced. And I have separated 8-bit and 16-bit version. I'm kinda doing on the 386 on the Game Boy Advance, I'm doing the same trick. I'm rendering the object in a smaller window. And no, I'm rendering it in a buffer that fits exactly the object. I used to copy it in a big frame buffer and then show the frame buffer. Or, okay, on the Game Boy Advance you don't need it, but on the 386. But now I'm rendering directly to the VGA, but in a way that clears the previous. It doesn't leave dirty pixels. And that work well if you want to make a demo with an object show that displays some objects in a distance. It might be okay. If you want to do a real engine, you might need to go the full frame buffer approach. But this one makes things a bit faster for all of the machines. Let's see the Game Boy Advance. Now, the emulator is faster than. It's a bit slower on the real GBA. I have enabled here. Yeah, let's. I have seen that somewhere. There are some, yeah, wait state stuff. I'm calling this, am I not? Yeah, I'm calling it. That would reduce the wait states in the cartridge and the RAM or something like that. I don't know if they are the best value, and they make a big difference. Also, back in the days when I started programming on Game Boy Advance, I didn't know that, and things were 3 times slower. If you don't know that, also, I have. I have put prepare edge list guru and especially the ones that the rasterizers. I've put them on. Oh, hold on. I disabled it. I have commented this out. This is in. Oh, I know. Because if you put everything, it's filling the IW RAM. That's the internal RAM, 32 kilobyte RAM, and it doesn't compile. Okay, I guess the 16-bit version might be a bit faster. Yeah, I forgot. So I'm not looking at the best case, but okay. Because the Game Boy Advanced, I learned it has an internal 32 kilobyte RAM. If you can upload coded data there, it does make a difference. Now this is the 8-bit version and it's still fast, but it could be faster, especially. But okay. I guess I'm not going to recompile it. It's pretty good on the GBA, and I have, because the GBA has smaller resolution, I have scaled it up a bit. It used to be a bit further compared to the other machines. I put it closer to compare. And again, if you go there, something's broken. Okay, that's the problem with the IW RAM. You have to decide what to upload. And I don't know if you can upload code and then unload code. I don't know yet. So the 16-bit version is IWRAM optimized. Of course it's a 16-bit version, so it might be slower, not much. I think this cube, like you see, here it does 45 usually. It does 37 on the real hardware for comparison. Yeah, you see the same. And then this object. And then if you... Oh, wrong button. Where is it? If you move it away, it's faster. Because I'm doing... Not only I'm rendering the object in a small... But I'm also rendering it back on the frame buffer. I'm rendering the small region of... I'm not doing a full frame buffer copy. Now if you move here... Because see, it's funny what kind of bugs we get. Because I have not, as I said, there is no polygon clipping. And it's going to overflow in memory. There are still things to fix. I guess that's it. And now I might show you how it runs in the real machine as much as I can. Either by video capturing the device or putting a phone camera on the screen, which looks bad, but okay.
Mm.